Good evening, one and all. My name is Naushad bin Jamal. It's my pleasure to introduce you, Professor Jamal Basran. Dr. Jamal Basran is a professor in the Department of Civil, Structural, and Environmental Engineering at University of Buffalo, which is a state university of New York in USA. He graduated in 1982 from Yildiz Technical University in Turkey, and he has two master's degree in civil engineering, first from Middle East Technical University in 1985 in Turkey, and then from Massachusetts Institute of Technology in 1988. His PhD was on engineering mechanics from the University of Arizona, Tucson in 1994, and he was the founding provost, the senior advisor to the president for University of Tabuk in Kingdom of Saudi Arabia during 2009 and 2015. Professor Jamal Basran is working in University of Buffalo in New York since 1994. He has expertise on various fields such as microelectronics, power electronics, damage mechanics of various materials like carbon nanotube, solid joints, particular composites, multi-scale modeling, fatigue of metals, materials, etc., and rate-dependent behavior of metals, etc. He is in the editorial board of several international journals like International Journal of Materials and Structural Integrity, AICTE Journal for Nanomechanics and Micromechanics, Advanced Nanobiomaterials and Devices, Journal of Advanced Engineering, Entropy Applied Mechanics, Materials, etc. He has introduced a theory to unifying Newtonian mechanics with the thermodynamics, and he has authored a textbook on that named Introduction to Unified Mechanics Theory Applications. He obtained this Fulbright Specialist Award for this year, and with that, this event was expected to be offline. Unfortunately, pandemic came again. We hope that he will be physically present in May, June 2022 this year, and giving an advanced lecture on the present topic. I welcome you, sir, to give this introductory talk on topic mechanics of materials and modeling. Thank you, sir.
Oh, thank you very much, Nashad, for the nice introduction. I'll share my screen now. So I am going to start today with, first of all, good morning or good evening to you, and then good morning to me. It is 9 o'clock in the morning here, and I know it is nighttime there. So I'll start with the basics of mechanics and explaining the unified mechanics theory basics. And I'll explain the objective, introduction, the literature in mechanics theory, experimental proofs, and recent work in the literature, and then conclusion. So what do we do in mechanics of materials? And of course, when we say materials, we mean everything. So we try to establish laws of nature governing behavior of inorganic and organic materials and structures during their lifetime, and hopefully without the need for phenomenological empirical models based on test data. Now, you know, my research has been primarily mechanics of electronics, electronic structures. Like there is a silk, for example, a solder joint in your cell phone. When it is brand new, it looks like this. And after a while, it will break. It will look like this. So in mechanics of materials, our objective is to predict this behavior by mathematical models. Now, what do we use for our mechanics of materials? We have laws of Newton, which he published in 1687, the first law, which is also known as the law of inertia. And then the second law, which is F equals ma. And the third law, action, reaction. Actually, this law was written by Hooke 10 years before Newton. Newton published his work in 1687, but Hooke came up with this law in 10 years before him, in 1678, or 9 years before him. And then these are the equations that we use to solve any system. Now, however, there are problems with these Newton's laws. The shortcomings: number one, there is no concept of energy loss or degradation, or as we call in thermodynamics, no entropy generation. For example, if we use the second law to calculate the initial acceleration of a soccer ball, so the acceleration will be force divided by mass of the ball, and force is the kick. The player kicks the ball, and then you get an acceleration. But however, according to this equation, this acceleration remains constant until eternity. It never degrades because there is no energy loss in the equation or degradation of the ball. Well, of course, that is not true, right? If you kick a ball, the ball will come to a stop. So that means that the Newton's second law can only tell us what happens at the initial second. But what happens after that initial second is outside the laws of Newton. And then if you look at his third law and Hooke's law, if you have a spring or a structural frame, if you are a civil engineer, the displacement in the spring or the frame is force divided by stiffness, right? But however, here this displacement remains constant whether the stiffness, whether the spring or the structure is 1 day old or 1,000 years old. Now we know that, of course, over time, the stiffness degrades, things get old, and the stiffness gets smaller and displacement gets bigger. So again, this Newton's third law will only tell you what will happen. And in Hooke's law, in the first second, you finish the building, the spring, but it doesn't tell you what happens actually next day, because next day, that spring or that frame is a different building. It has aged, so there is no energy loss or degradation. Now, so what do people, then we also have laws of thermodynamics. First law is conservation of energy. We assume energy is conserved in a closed system. And the second law, which is also known as entropy law, in a natural process, the sum of entropies of the interacting system increases, and entropy of an isolated closed system never decreases. And entropy generation rate is minimum when entropy is maximum. Now, simplest description of entropy is energy unavailable for work due to dissipation or loss or degradation, and cannot be created but cannot be can be created but cannot be destroyed, opposite of the energy. You cannot create energy, but you can create entropy. You cannot destroy you cannot destroy entropy. Entropy generation is always positive. It means that system will always age, will always get older. It will be able to generate less entropy or the generation rate will get smaller and smaller every day. It is not possible for any closed system not to have a positive entropy generation. Essentially, in nature, everything ages, gets older and older, and then finally fails or dies. So this is the second law. Now, the second law, the only mathematical formulation for the second law of thermodynamics was formulated by Boltzmann. And he showed that after mathematical derivation, intensity of entropy per unit mass is equal to K, which is a constant, Boltzmann constant, times omega, which is the number of microstates, he said. But what he did actually in his formulation, it shows that there is a natural tendency of any isolated closed system, living or non-living, to generate into more disordered state. So the state continuously changes. And then after a while, the system dies. It can no longer generate entropy. So the irreversible entropy generation rate becomes zero. The system reaches the end. And it is not possible to reverse this. So you cannot get rid of this generated entropy. You cannot go back. You cannot take somebody 80 years old, make them 20 again. You can give them a very good plastic surgery, and then they may look like a model in Paris at 80 years old because of the plastic surgery, but they will still have a heart attack and die next day because the system has irreversible entropy generated, which cannot be reversed. So, and this is also called statistical mechanics. So entropy is an extensive property of a thermodynamic system, and it is related to a number of microstructural configurations, microstates. So what does microstate mean? Let's say, for example, let's say I have a cylinder, concrete cylinder sample that we test in our classes, right? It is 15 inches in diameter, and then 15 centimeters in diameter, and then 30 centimeters in height. You apply compression and you fail that concrete sample, right? Now, let's say at the initial point, before we break that concrete sample, we number each gravel, each sand with a number, and then we define their coordinates with GPS. Let's say we put a GPS circuit in each one. So after you apply the load, each gravel, each sand particle will move to a new location. That new location is a new microstate. And then you keep increasing the load, they will move to a new location. That each one is a microstate. And those in this equation, the omega represent the microstates. And that number of microstates that the system can take is governed by this equation as shown by Boltzmann's formulation. Now, after Boltzmann died, Max Planck in 1901 actually showed that instead of using the number of microstate, if you use the probability of a microstate happening, omega, which is the initial for Wahrscheinlichkeit, which is the German for probability, he ended up with the same equation. So you don't need to worry about the number of microstates, just the probability of a microstate, because it's always easier to deal with the probability of a state happening than number of states dealing with which. Now, Boltzmann published this equation, initial equation, in a book called Theory of Gases. And from 1877, I'll say until 1997, nobody bothered to read the book is written in German, not in English, rederive this equation or go through his formulation. It was assumed that it is just for gases. But when I went through it, I was able to first see, and then later on in the last 30 years, prove that this equation is not actually for gases. It is true for everything. Because he does, in his, if you go through his derivation, he doesn't make any assumption that would preclude solids or liquids. If you have solids or liquids, you can have less possibility of states, because if two particles are attached to each other, number of microstates can be less, but the equation will give us the upper bound. So regardless of the matter, liquid, gas, fluid, the equation is true. So then I wrote my book. I did the derivation all over again, starting from scratch. And I prove that, so actually this formulation is not restricted to gases. But it does give an upper bound value for solids. So how does entropy and the degradation are related in the material? Starting with Boltzmann's approach, he runs a very, very simple example. Let's say I have a box, okay? And then I have 4 balls in this box, A, B, C, D. So assuming that we are using the English alphabet, so these balls are in order, okay? When I shake this box, and then I get next one, A, B, D, C, this is another possible state, and that is a disorder. So order and disorder are relative terms. But however, it changes from the initial order. But what is important is to go from this state to this state, you have to consume energy. And because energy cannot create it, so that means you generated entropy. So this change in the order is proportional to the energy that you consumed. And there are only 24 possible combinations here, and you cannot generate any more combinations. And of course, here we are assuming that this is like a gas, and A, B, C, D atoms are not attached to each other, okay? But however, as a result, you have 24 possible combinations, which is Boltzmann's formulation. But let's say I attach A and B together with a wire. So then I will have, instead of 4, I will have 3 independent systems. So as a result, I will still have a disorder, but I will have not 4, but I will have, instead of 4, I will have only 6 possible states. So as a result, the formulation is valid for any system, regardless of the matter is in it. Now, so I have been working on this for this 30 years. And then in 2015, 2 professors from University of Pennsylvania Medical School published Kim Sharp and Franz Machinsky translation of Boltzmann's paper, the original 1877 paper. And they concluded that exactly the same thing I have been saying, that the Boltzmann's formulation is not for gases only. It is for solids, liquids, and gases, for everything. Now, when we do formulate the mechanics of materials, we have to, of course, use these 2 laws, laws of Newton and laws of thermodynamics. Laws of Newton provide the response of external disturbance in space-time coordinates, but it does not account for changes happening in the system like aging or energy loss. Now, just to clarify, when I say Newtonian mechanics, I mean everything that is using universal laws of motion of Newton, like Hamiltonian mechanics, Lagrangian mechanics. These are all derivatives of Newtonian mechanics. If you take one derivative of Hamiltonian, you end up with, again, Newton's equations. But they're based on the 3 laws. And then laws of thermodynamics, which provide information about the microstructural changing and energy loss, degradation happening in the system along a thermodynamic state index axis. I'll explain what is thermodynamic state index axis. Now, historically, when we do mechanics of materials, it is easy to use laws of Newton to model a material. What do they do? You take a material, you test it, you get the stress-strain diagram, and then you curve fit to that stress-strain diagram, so you have the stress-strain response, and then you use it in an equilibrium equation. But how would you degrade the system over time? They cannot. So again, they do testing to see amount of energy loss, and then you create an empirical equation, and then you use the data that you obtained from testing to model the system. Now, of course, that is not very scientific, because essentially you are curve fitting to test data. Actually, you don't need to do analysis because you already did the testing. You already have the answer to the question. So, for example, in dynamic equilibrium equation, this concept of C, the damping, is actually to introduce dissipation into the system. But however, it is completely empirical. It is not based on any physics in this equation. You do free vibration testing, and then you get the damping of the free vibration, and you use that slope here for the damping of the system. So it is completely empirical. That is how historically we introduce energy loss degradation into Newtonian mechanics. And other methods are Weibull plots, Miner's rule, Coffin-Manson relation, Paris law, Gerson model, Gerson-Twergaard-Needleman model, Johnson-Cook model, continuum damage mechanics model, structural fragility curves. Essentially, you introduce energy loss degradation into Newton's universal equations of motion by these empirical methods. You do an experiment, you get the data, you curve fit to a polynomial, and then you put it into Newton's equations. So they're all based on phenomenological curve fitting techniques, and test data is needed beforehand to generate a potential or a polynomial. And of course, these potentials and polynomials are not universal for all load types, loading paths, material types, or temperatures. For every different loading path, you have to get a different test data. So it is not very scientific. It is completely phenomenological, because they have not been able to introduce thermodynamics into Newtonian mechanics directly as laws. But it has been known that irreversible entropy generation and disorder are governed by laws of thermodynamics. It is not that they did not know, for we know that they knew that externally applied energy will lead to permanent changes in the microstructure described as a positive entropy production. And in solids, degradation happens due to irreversible internal entropy production. This has been known for the last 150 years. And a disordered state is formed from an ordered state and through irreversible entropy production. And the change in the entropy are naturally related. So that going from one state to other state is directly related to the entropy, the energy that you lost. Professor Jim Rice, one of the biggest names in mechanics at Harvard in 1971, he wrote in a paper in JMPS, at any given temperature and pattern of internal arrangement within the material, the rate at which any specific structural arrangement occurs is fully determined by the thermodynamic forces. So he could see this, but unfortunately he could not formulate it in this paper. So now what we are going to do is we are going to introduce laws of thermodynamics directly into laws of Newton to create a new law. It is like a marriage between two individuals, but the new family is different than each as an individual. Now, so in order to be able to do this, to introduce primarily the first law of thermodynamics and the second law of thermodynamics, you have to convert the second law of thermodynamics into an axis that will allow you to take derivatives, because laws of Newton are derived in x, y, z time space. in XYZ time space, you cannot have thermodynamics because there is no access for thermodynamics. I will show you with a figure later on. So that means first we have to modify that space. So we introduce a new axis called thermodynamic state index. So at any given time, at any system, a human, a car, computer has a thermodynamic state, and its state of this system is defined by an index between 0 and 1. And you cannot be outside this range. When it is born 0, and then it is dies 1. So we say phi is this thermodynamic state index variable, and then it has the initial entropy. It can start with the initial S0 can take it 0, or it can start from an initial value if it has an initial disorder, and then it has an associated disorder with that initial state, and then it will go to a next state S, and then associated disorder W. So there is always a difference in disorder from initial state. So then this thermodynamic state index will go from 0 to 1 according to this Boltzmann's entropy formulation. So essentially this equation is nothing but a normalized form of the second law of thermodynamics as defined Boltzmann's entropy formulation. Now, it means S minus S naught is the change in entropy. This is a molecular mass, Avogadro's constant, Boltzmann's constant. So I just need to calculate this between two states. Now, in thermodynamics, we know that if we know the state, initial state of the system, and then given, if it is a closed system, we can calculate what will happen into the system if you apply loading. And this is the main concept of thermodynamics. Like, for example, if I have a chamber here and a chamber here, it is separated by a wall. P is pressure, V is volume, N is number of atoms, T is temperature, and C is concentration of the chemical. And this chamber has a different values. If I remove this, okay, these two will mix, and then we can calculate what will happen, the final state, using laws of thermodynamics. So essentially, if you have a system, whether it is gas or liquid or state, you have state variables. Okay, you have state variables. And then if you're applying a loading from outside, we treat the system as a thermodynamic system by deriving the fundamental equation of the system. We can calculate what will happen without resorting to testing. So the basic, Callan in 1985 wrote one of the best thermodynamics textbooks that I know of. He says the basic problem of thermodynamics is the determination of the equilibrium state that eventually results after the removal of internal constraints in a closed composite system. Because after you remove this barrier, separation wall, these two will mix and they will reach an equilibrium state. Like temperature here is T1, here is T2, but they will stabilize. And thermodynamics allows us to calculate that. So the basic problem can be solved if the entropy of the system is known after we remove this separation wall as a function of the intrinsic parameters of the system. So the intrinsic parameters of the system here are these. Now, so that the relation that gives the entropy generation as a function of the system parameters is called the thermodynamic fundamental relation, or thermodynamic fundamental equation. So we can derive from physics, without any test data, how these two chambers will come to an equilibrium state. And you don't have to do an experiment to tell me what would happen, and then I can curve fit a polynomial to get the equilibrium state. So therefore, follows that if the fundamental relation, thermodynamic fundamental relation of a particular system is known, all conceivable thermodynamic information about the system can be obtained from it. It refers to this thermodynamic relation. Essentially, if the fundamental relation of a system is known, every thermodynamic attribute is completely precisely determined, from Callan 1985 textbook. Now, where is this fundamental relation? Okay, that relation is not available in textbooks or in papers. You have to derive it from mathematics for the system, from physics and mathematics. So that requires a derivation. You have to understand the system and derive the fundamental relation mathematically. So, in simple explanation for thermodynamics, thermodynamics says everything in nature exists on an energy terrain. Okay, let's say we have a terrain like this, okay, hills and mountains and valleys. So all organic and inorganic system exist on an energy topology. If I drop a ball here, what is it going to happen? It is going to come and stop at one of the valleys, right? And then let's say somehow I put a ball here at the tip of one of the hills. I balanced it for a second, and then I kick this ball. When I kick that ball, the thermodynamic state index is 0. And then that ball will travel, and then will come to a stop in a valley. At that point, thermodynamic state index is 1. So if I know the thermodynamic fundamental equation of the path taken by this ball on this terrain, right? And it can take many paths. I can exactly calculate how far this ball can go. Now, but you can say, well, you don't know, it might be able to go, if it goes downhill, it will go 100 meters. Here it will go on 10 meters because it is going uphill. Exactly. That is what the thermodynamic fundamental equation will tell me. It will give me the probability of each state. But what will not change is the thermodynamic state index will be 0 at the beginning. It means I have the initial energy to consume, and then when it stops, the energy will become, that initial kick is completely consumed, and thermodynamic state index is 1. That cannot change. So then we can marry these laws. Now, we don't have first law of unified mechanics theory because we are marrying the second law of Newton and second law of thermodynamics. So it doesn't make sense to call it first law. The second law says degradation of initial momentum of a body takes place according to the second law of thermodynamics. The rate of degradation of energy is directly proportional to the entropy generation rate along the path chosen. So this piece is modern definition of Newton's second law, F equals ma. As you know, actually Newton's law is not valid for variable mass systems. So mass is constant with respect to time. It goes out, so dv over dt acceleration. But however, that initial acceleration will degrade according to second law of thermodynamics. So this becomes the second law of unified mechanics theory. But of course, when you unify these two laws, the derivative of displacement or velocity with respect to entropy is no longer zero because you have a new axis. Again, this is a pictorial description of this law. So at this point, phi is 0, a is equal to fm, but however, at any point, the acceleration is governed by this equation, and then here, phi is 1, and the acceleration is 0. Now, the second law of unified mechanics theory doesn't just govern the initial moment like Newton, but it governs the entire travel, entire motion of the ball. And the third law of the unified mechanics theory, again, combining the third law of Newton and second law of thermodynamics, to every action, there is always opposed and equal reaction. The initial reaction of a body in response to an action will change over time as the stiffness degrades according to the second law of thermodynamics and its thermodynamic fundamental equation. The reaction will be governed by the third law of the unified mechanics theory. So this reaction is first derivative of the energy, but however, here K will degrade over time. And then displacement will get bigger. If you have a spring, for example, if you uploaded, unloaded a million times, or not million times, 1,000 times, the stiffness will degrade and finally it will fail. It will break in two. That is what fatigue is. So if dm over dt is negligible, just for mathematics, you can write it in this form. And then you can write the third law in this form. Actually, in this term, d phi entropy with respect to u is not zero. But if it is just a small deformation, small strain problem, can be small. But this term, derivative of entropy with respect to displacement, is not zero. This term is zero in the Newtonian mechanics. So just comparing the Newtonian mechanics theory laws, F equals mu double dot FKU, but then in Newtonian mechanics, unified mechanics theory, they change. Now, I'm gonna show you this and stop here for today and get your questions. So we said Newton's equations of motion are derived for x, y, z, and time. And therefore, they don't account for thermodynamics. And then historically, when people use Newtonian mechanics to account for energy loss, they use phenomenological degradation in the equation, but still within the x, y, z time space. But still, the derivative of displacement, when you change the displacement, you cannot generate entropy. So actually, they do not satisfy laws of thermodynamics in the strict sense of mathematics. They just jump discretely from state to state without satisfying the laws of thermodynamics in the Newtonian mechanics. Now, in the unified mechanics theory, thermodynamics has its own axis. Okay. Now, let's say I have a 5-year-old boy and 100-year-old man, and then in Newtonian space, I can put them in their x, y, z coordinates, and then on the time scale, they go to 5-year-old and then 100-year-old. Again, I can define them. But however, let's say the 5-year-old has a stage 4 cancer and he is expected to die next month or next day. And then 100-year-old person is also very sick and is expected to die very soon. On this axis, thermodynamic state index axis, because this can only go between 0 and 1, they are equal. They are both at 0.99, even though they are at different points on the time axis, they are at the same point on this axis. Because the information that is represented by this axis cannot be represented in the Newtonian space, so therefore this axis is linearly independent. As a result, the derivatives with respect to these axes are also not zero. So then this changes, of course, many things compared to traditional mechanics formulation, because we have a new axis. So I want to stop here for today, and then I'm gonna stop sharing my screen, and then I would like to ask if you have questions in the rest of the time. In the chat, okay, I'll read from the chat. Okay, I'm gonna read from the chat your questions. How do we obtain energy topology for a material? How is it plotted? Okay, so we have to have the material properties, and then we have to have we have to derive the thermodynamic fundamental equation of the material, and we have to know our loading. Do I have a mechanical load? Do I have a thermal load? Do I have an electrical load? Do I have a radiation load? And they define your topology. And then next question is, a spring is supporting a load, F equals Kx equals mj is the state of equilibrium. What is the energy landscape for this system? The energy landscape will change as you change the force. Essentially, the system will move depending on the force, and then if the force is smaller than what the material can carry, it will stay in the stable state, or you can go to the unstable state and you can break it in two. So we always operate in an energy landscape. Actually, that is what you do in finite element analysis, right? What if the spring is degrading due to applied load, how can it be represented without doing experiment? So yeah, this is a good question. So what is the question is, if the spring is degrading due to the applied load, how can it be represented without doing experiment? So we don't need the experiment because we derive the thermodynamic fundamental equation of the spring. We say everything in the universe is governed by laws of thermodynamics. Spring is a thermodynamic system. So we derive the thermodynamic fundamental equation of the spring. So we know how the spring ages, how the spring degrades. We will have examples, so don't worry. If we are plotting energy against different states, then how are we plotting different states? That I don't understand that question. I'm sorry. Can we exchange the position of states on the plot? Well, to change position, to go from one position to another position, you need energy. You cannot move, you cannot do work without energy. If you apply external energy, yeah, you can go from one position to another position. Then want the energy topology for the same material change?
Sir,
I don't understand the question.
Sir.
Energy topology for the material within the stable system cannot change because essentially you have a system, and then the system at most it can break. So I don't know what.
Sir, my question is basically, I saw that energy topology curve was a 3D plot,
Yes.
and then different states are being defined by two different parameters. Is that the case?
No, not different parameters. They are defined by the thermodynamic fundamental equation of the system. Like I had two chambers, right? So I mix those chambers until they come to an equilibrium. They will keep traveling over the energy terrain, and then they will find an equilibrium point. There can be 10, 20, 50, or two thermodynamic intrinsic variables. It depends on the material. It depends on.
Sir, but what I cannot understand is we are finding the energy at different states and we are plotting the whole curve. But how are the states, the sequence of those states, is that well defined? Like, is their position?
Well, so let's say, let's give this example. Okay, let's say I have a spring. Okay, it has zero deflection. Okay, and then I put a load on it, 10 kilogram load on it. Okay, so at the initial zero time, I have zero deflection and 10 kilogram load. Is this an equilibrium? It cannot be in equilibrium. I have 10 kilogram of load and zero deflection. So the spring has to move to a new point on the energy terrain to get into equilibrium with the load.
Yes, sir. Okay.
And then I increase the load again. Let's say 10 kilogram gave me 1 centimeter. I increase the load to 50 kilogram. And then my displacement is 1 centimeter. It is still not in equilibrium. it has to find a new point on the terrain where it can be in equilibrium. So it has to, again, travel.
Okay.
But the travel cannot be a jump. It is not like, it doesn't happen over 0 second. If it is going from 1 centimeter to, let's say, 5 centimeters, it will first go to 1.1, 1.2, 1.3. It will slowly stretch. Right?
Okay, sir. Yes, sir.
Yeah. Okay. Let's go to the next question. It is understood that entropy generated keeps increasing with time until material failure occurs. However, I could not understand the entropy generation rate. Is the rate calculated with respect to time? Sir, can you explain? Okay, that's a good question, actually. So time and entropy, thermodynamic state index, are linearly independent axes. You can travel on time axis without traveling on entropy axis. Let me give you an example. Okay? At 0 Kelvin, or minus 273 degrees Celsius, all atoms stop. You can no longer generate entropy. But time doesn't stop. Time keeps moving, right? Time keeps moving. So therefore, entropy and time are not related, are linearly independent. One can move without the other moving. So the generation of entropy rate is purely a function of the thermodynamic fundamental equation of the material, how much energy this material has to lose. And if that is irrespective of time, like let's say the material has 100 kilojoule energy to lose, I can take this 1 joule at a time, or I can explode it by burn it and take it out in 1 second. So the generation of entropy rate is independent of time. Let's go to second one. If I have 4 balls in a box, we have total probability of 24, which is constant. Then how can we say that entropy is increasing with time scale? Yeah, but you don't get all those 24 possibilities by shaking the ball 1 time. If you shake it once, you get 1/24. If you want to get 2 of those possibilities, at least you have to shake it twice. But in the essentially, there is amount of energy you need to spend to get all 24 happen. It doesn't just go from 1 to 24. So you cannot get free lunch. You have to consume energy to be able to get all 24 happen. If a material has high entropy value, does it mean stable or failed? Okay, this is a very good question too. So in thermodynamics, first of all, if it has a very high entropy value, it means that it is at a stable state. But a failed material is also at a stable state because it doesn't generate any entropy anymore. So what it means is essentially on the energy landscape, the system is sitting in one of the valleys. Like, for example, let's say we did work a few years back to a company who makes particle-filled polymers as a kitchen countertop. But when people put hot pot on the kitchen countertop, the counter will change color. And then later on, it will get stained with the color change. and then they had a 10-year warranty. They had to replace the whole counter. So when we did the analysis for this, our so-called failure definition was change in color. How much heat did you have to put to change the color on the system? There was no crack or failure or anything, but the color would change and then it would stain it. So that was the definition of failure. So for any thermodynamic system, going from one state to another is just another disordered state. Failure is a completely arbitrary. But at the final state that we define as our last state, entropy will be maximum, entropy generation rate will be 0. For a closed system, of course. Okay, so okay, I have questions now from Dr. Kayuri Joshi.
Yes, sir. So while this, unified theory gives us satisfaction of understanding these failure theories and tying up the mechanical, phenomenological equations with the, let's say, fundamental principles. But would it be ever practical to, use it to, design anything, right, of value? Because it's not really possible to identify all the parameters needed to define a thermodynamic state and thus the entropy. So while there is theoretical value to it, but whether it will be any have a practical value.
Yeah. So one of the, I don't want to give company name, but one of the biggest computer chip manufacturers in the world is actually using this theory to design their chips. So deriving the thermodynamic fundamental equation, yes, it does take some time, but at the end you derive it and then you put it in abacus and you have it. So so it is actually used by very large manufacturers in the US. Okay, next, Dr. A.K. Singh.
Hello, Professor.
Yes.
It was a very interesting talk, and as far as my first question is concerned, I got the application of this theory, because suppose some theories, then people ask where it is application, so I got the answer. But I have another just curiosity, how this idea is going to be useful in that Schrodinger equation that deals with the quantum mechanics. Do you have any opinion?
Yeah, okay, so the laws of thermodynamics that we just discussed are valid for near equilibrium systems. So in quantum mechanics, still the question exists, are we near equilibrium or far from equilibrium? So this derivation is only valid for continuum mechanics. I have not done any work in quantum mechanics. There are some people, we have a group on LinkedIn called Unified Mechanics Theory Group, and there is one scientist there who believes that this can solve all the problems in it can solve all the problems in quantum mechanics by having the fifth axis. But I myself have never published or done any research to study application of this fifth axis in quantum mechanics.
Yeah, right. Thank you, Professor.
Oh, thank you. Okay, I think I have one more chat. Okay, how do we think of strain path, stress path dependent failure of materials in this new framework? Essentially, everything comes to the same based on entropy. Failure of material may not be the closed system. Interaction with environment is possible for me. Well, let me answer the second question first. Yeah, so if there is an interaction with the environment, it means there will be generation like corrosion, for example, We are working on that problem right now. The interaction with the environment will also add to your entropy generation, and that interaction has to be part of your fundamental equation. It cannot be ignored. The stress path and strain path is very important because still we are using the, if you are using plasticity, in the theory of plasticity, plastic strain is a function of load path. So therefore, each load path will give you a different entropy generation. So therefore, the results will be path dependent. It is not independent. Like, for example, let's say I derive the thermodynamic fundamental equation for a human being. Okay? I can tell you how long you will live. But however, in my equation, I have to know if you are gonna drink 2 bottles of whiskey every day and consume 5 packs of cigarettes and use heroin, or you are free of drugs and exercise every day and then live peaceful, stressful life. And then I can tell you how long you will live. So essentially, the load, the approach to life you have taken is input to me, is like a load. You have to tell me what the load is, then I can tell you what the output is. But I know that in electrical engineering, they call it the transfer, black box transfer function. You tell me what is the input, then I will tell you what the output is. So that depends on the user. You tell me what the load will be on the bridge, then I will tell you what will happen. But my fundamental equation accounts for everything, whether it is gonna be an explosion or it is gonna be regular traffic. I just need to know what that is. Okay, I think we are done.
Yeah.
And my time is up. Is there any other question I didn't answer? I don't see any hands up. I don't see any chat. Well, thank you very much.
Thank you, Professor Jamal, for this insightful lecture on introduction to unified mechanics theory and a very good discussion on the topic. I thank all the participants for making this session very interactive and very informative.